Hello. Welcome. So things have changed. I did a fair amount of work off camera. Some of it I probably could have done on camera, but yeah, things have just been crazy of late, and I have not really had the energy to record a video. So apologies for that, but I did want to tinker on this in the meantime. So what you're looking at on the right is the front panel, at least what's been completed so far. There's a bit of empty space in here for extra things that I'd like to add in the future, but haven't quite been implemented yet. You can see that it's displaying the instructions down here, and you can see the program counter here. I guess I could actually make it a little bit bigger so that it's easier to see. Instruction display down here. We've got the two registers here. We've got the immediate, if the instruction takes an immediate. We've got destination register down here. I'm not 100% sure it's always accurate because, for example, NOP has that, but that's something that we can fix in the future. And then we've got the left, or the L bus and the R bus down here. And in here, I'm going to put the ALU up, probably. So the point of this episode is actually to work on the ALU. So I don't want to go into too much depth on what I've done here off camera, but very briefly, I've pulled a few more of the control signals out of the CPU. I've also added a few more options for ways to run the CPU. So if we run here, there's a slow clock that'll run fairly slowly. And then you can also hit run here and it'll run as fast as it can. So there's that. And then there's a bit of a configuration here to change the speed of the slow clock for the FPGA. That way it can be much slower on an FPGA, whereas this simulation runs fairly slowly. So in here, this circuit obviously has changed quite a lot. I'm not 100% sure that this is a good circuit, but yeah. Mainly there's a counter here that will strobe the step line at a certain interval. That way I can easily make the processor run slower on an FPGA. So that's what's going on in here. And the decoder has the immediate going out to some pins. So then I can display what the immediate is and whether or not it's valid. So in the front panel, lots of pins here, and the VGA blinking lights has grown into somewhat of a forest here. Inside here, this has gotten dramatically hairy, and I'm really not happy with this because as I add more things in here, it just becomes slower and slower. There is much better ways of doing buses like this in an FPGA, and this is really not the best for this number of peripherals on the bus. I'm not sure how much I want to fix that right now. And if I do fix it, I'll probably fix it on camera. But I feel like having too many episodes on the VGA part of this, as opposed to the processor, is probably not a good thing. So I think I'll leave fixing this to a later episode. The other thing I had to do was it was crossing clock domains. So I had to take both clocks and do a bunch of registers to cross the clock domain properly. Otherwise, it just kind of glitches. You really only see it when it's running at max speed, but still, this is more proper. And while I was at it, what I did is I made the fast clock domain register gated by the vertical blank. So it'll only update these registers when it's not drawing on the screen. And that just prevents any glitching and keeps everything stable while it's drawing. So that's what I did in here. I'm not going to go into all of the details here, but it essentially just draws the picture that you saw earlier with all of the information on it. So we've got program counter, the 4 registers that we currently have, and we're going to have 16 registers. So this is going to grow dramatically when displaying all 16 registers. the RD register, RS, and then RD is actually duplicated twice because I wanted to display it in 2 different locations. And then we've got what's on the L bus, R bus, the opcode, etc. So again, I'm not going to go into too much detail on this because that's not what this episode is about, but I'm going to do some thinking about a better way of doing this sort of display in an FPGA. I don't really know what the better way of doing this would be. If you have any ideas, feel free to leave comments down below. I'd be very curious. Anyway, enough rambling about that. In this episode, I'd like to go into the ALU, and I've already recorded this footage, so it's on a previous version before I did the VGA circuit. So bear that in mind. Yeah, so let's get right into it. We've got this execute unit here, and it's sort of got a half-baked ALU in it. It sure would be nice to have a proper ALU. Currently, this is kind of, well, what's actually going to happen with this comparator is it's going to do a subtract. And the same thing with this one. So we actually have quite a bit of logic in here when it's not necessary. It could be, well, I don't want to do any optimization yet. I'd like to do the simplest thing that could possibly work, but it would be nice to have proper flags. And in order to do that, we need to be able to subtract, is basically what it comes down to. So, subtraction. Well, how do you do subtraction? If I put, say, 42 in here, and I subtract 5, notice what happens to these checkboxes here. So -5 is actually all of these bits turned on, except for this one right here. So if we wanted to make this positive, so we remove the sign, we'd have to convert this into this. Well, what's the difference between these? You'll notice that all of the bits are flipped, but this bit here doesn't seem to flip, right? So what's the difference between these 2 states? Well, it's just flipping all of the bits and adding 1 is what the difference is. So how could we flip all of the bits on R and add 1? Well, the adder has a carry in, and that adds 1 to the result. So we just need to make sure that this goes high and this is inverted. So let's see if we can do that. Okay, so here's our addition, and if we hit this, it subtracts. So that's subtraction, basically. So given this, what do we need to do in order to calculate all of this? Well, let's make some room here. Okay. Let's just move this all over here. And then, all right. So I have a bit of a cheat sheet and the instructions over here. Here's what we need to do. And I haven't decided to do this, so I'll just delete it. And these ones I renamed. This was higher same, and this is low. So we could do these really easily because we have a carry bit that comes out of the subtraction. So higher same, I think I have these backwards probably because we want to invert it because we want to skip when this is false, right? So if higher same means carry is 1 probably. No, maybe I already did flip these around. If it's less than, it should carry actually. No, these are backwards. No, actually. So if it's not equal, then the Z flag, which is 0, should be 1. And then we should have 0. If it's equal, if it's equal, then subtracting them will produce 0. So this flag was correct. Maybe it did flip them around. Well, it'll be easy enough to tell. if we got it backwards. So these two should be really easy. This is a little bit harder, but we just need to detect 0. And then this is going to be tricky because n is the negative. Negative is easy, but overflow is not easy at all. So let's do that. Carry. Okay, so we've got our carry, and that handles these down here. So now, which one was which again? Higher same is carry is 1, low is carry is 0. Low is carry is 0, so this needs to be inverted. Now, what we need to do is we need to get the microcode to subtract. The easiest way would just be make one of the bits the subtract bit on the up here. So okay, so rearranging that a little bit, our move instruction is now at 3, so we'll need to change that. Our NOP is still at 0, add is still at 1, and subtract is just setting the higher bit. So that would be 4. 4 is subtract. So let's update our microcode for that. First, let's make sure it runs. Yes, it does. Microcode. So we said move is now at 3, and we have a subtract now at 4. Okay. So I just made the microcode. Now, what do you figure the chances are that everything will just work first try? Don't think it will. Well, run all tests. ALU ops failed. If low and higher same failed. Okay, well, those two failed because we now need to subtract. We actually don't have any microcode for that. It just sends a 0. Where are those in the opcode space? I think it's in here. Okay, so if 1100. Okay, that goes here. Oh, there we go. Now does it pass? Add failed, jump failed, if eq failed. What did I do? I think I know. Well, let's try this. We got 42 and 5, and we have opcode 4. What is this doing? So 42 is still coming out here. We've got low. So low. It's not lower than. Higher same. So this isn't actually emitting the subtracted value. If we want the subtracted value, we need to do 5, I think. Yeah, and then it'll emit the subtracted value. So what we're actually doing is a compare, which is what we want. Higher same, if higher same, skip. Right, right is lower than. So yeah, I think this is correct. Our microcode is slightly incorrect though. This is not sub, this is compare. Let's just spell it out. And if we want actual sub, it is actually 5. Okay, that's actual sub. This is compare. I think that's correct. These are still failing though. What happens? Move, add. This is doing what I'd expect it to do. Oh, but the compare didn't work. Oh, I think I know. Yeah, I do know. I know. Here we go. So for this, we're taking the inverted output and we're now subtracting, which is not quite what we want. So temporarily, we need to do this instead. That should fix it. And this should count up to 14 and then reset everything. And it does. Yay, okay. Run on tests. This is, well, that's not expected. It should work. Maybe we got them backwards? There, now they pass. ALU ops failed, but I can fix that later. Okay, so we've got the carry flag. Now we need a 0 flag so we can do equals and not equals. Well, we just want to know if the output is 0, right? Now, if you XOR two numbers together, if they're equal, you'll get 0. If they're not equal, you'll get something other than 0. So we can pull some of these out. I'm still going to use a comparator, mainly because it's probably the most efficient way to do this on a FPGA, just because this will be boiled down to just an equals operation. So it's going to be 16 bits. And we're just checking if it's 0. Okay, that's pretty straightforward. Let's wire this into our OR gate. There we go. Okay, well, our test suite passes, which is good. I'm not sure what's going on here, but awesome. So doing a sign comparison is a little bit more tricky because I need to produce the overflow flag. Overflow flag is a little bit tricky. I don't think trying to cram it into this episode is a good idea. Plus, we have other things that we need to build in the ALU, like a logic unit. So I think that would be best to keep the overflow flag and then the logic unit for the next episode. So thank you very much for watching. I hope you have a great day. Bye.